We're going to get started now with our second to last talk. So we're very excited to have Jenna Rajchgot from McMaster University, who will be telling us about geometric vertex decomposition and liaison of toric ideals of graphs.
Great.
Go ahead.
Well, thanks, Oliver, and thanks very much for the great conference so far and the opportunity to speak. So yes, I'm going to tell you about some joint work with actually two groups. So the first half of the talk will be sort of joint background, which is joint work with Patricia Klein at the University of Minnesota. And then the second bit will be more recent work with a group at McMaster, Mike Cummings, who was an undergraduate research student last summer, Sergio Da Silva, who's a postdoc at McMaster, and Adam Van Tull, who's my colleague, another faculty member. So, oops, let's see. Okay. So I want to start off just nothing about toric ideals of graphs yet, but just sort of with two related viewpoints on the same families of varieties. So some ideals and varieties are popular among both, to be studied among both commutative algebraists and among algebraic combinatorialists. And some examples of this include like ideals of K by K minors. Ideals of K by K minors of a generic M by N matrix is the same thing as ideal defining an open patch of a Grassmannian Schubert variety. One-sided mixed ladder determinantal ideals, that's the same thing as Schubert determinantal ideals. So the ideals defining matrix Schubert varieties for vexillary or 2, 1, 4, 3 avoiding permutations. Two-sided mixed ladder determinantal ideals can be identified with certain Kaj-Dunn-Lustig ideals, which are defining ideals of Schubert varieties intersected with an opposite Schubert cell. So you can kind of see these very natural determinantal things, right? We know they show up in algebraic combinatorics as well, and certainly both communities are interested in them. And so what I want to start with today is just show that certain techniques used on sort of both sides of these correspondences are very closely related, okay? And the two techniques being geometric vertex decomposition on the one hand, introduced by Knutson-Miller-Yong, and Gorenstein Liaison theory on the commutative algebra side. So towards defining geometric vertex decomposition, I want to start off with vertex decomposition, and that's a notion that can be assigned to a simplicial complex. And so I want to start off with Squarefree monomial ideals in the Stanley-Reisner correspondence, which identifies Squarefree monomial ideals with simplicial complexes. So recall the Stanley-Reisner correspondence. Probably some of you at least are familiar with it. Between a Squarefree monomial ideal and a simplicial complex on a vertex set, given by a monomial, a Squarefree monomial, xi1 through xir is an element of the ideal, if and only if the set of subscripts I1 through IR is not a face of the simplicial complex. So for example, here's my ideal I delta, my Squarefree monomial ideal generated by x1, x4, x2, x5, and x1, x5. And the corresponding simplicial complex is this three triangles, filled in triangles glued together. And we see that x1, x4 is not a face, it's not an edge in this simplicial complex. 2, 5 is not a face, and so x2, x5 is in the ideal. And 1, 5 is not a face, x1, x5 is in the ideal. In fact, the ideal has minimal generators corresponding to the minimal non-faces. Okay, so that's the Stanley-Reisner correspondence. Squarefree monomial ideals correspond to simplicial complexes. Okay. Now, the idea here, of course, is that we want combinatorial properties of the simplicial complexes to tell us algebra geometric information about our Squarefree monomial ideals. And the property that I want to focus on, the combinatorial property I want to focus on, is called vertex decomposability. And that's a way of sort of recursively breaking down a simplicial complex into pieces. And we do it by this process of vertex decomposition. So at the very top of the slide, we have this definition of the link and the deletion. And so given a simplicial complex and a vertex of that complex, define the link to be the set of faces such that F union the vertex is in delta, but F intersect the vertex is empty. And the deletion to be the set of faces that don't see V. Okay, so in our example, right, my simplicial complex with these three triangles, the deletion is just all of the faces that don't see vertex 5, so it's these guys. And the link is 3, 4, right? It's all of the faces such that if I put 5 back in, I get a face of the complex. Okay, so what we see is that our original complex, delta, can be decomposed into the deletion and a cone over the link. Okay, a cone over vertex 5 of the link. Okay, and we say a pure, that is, all of the maximal faces are of the same dimension, simplicial complex is vertex decomposable if either delta is a simplex or delta is empty, or there exists a vertex such that the link and the deletion are vertex decomposable. So it's this recursive process. And the theorem is that if we have a vertex decomposable complex, then the associated ring, the Stanley-Reisner ring, the polynomial ring mod the ideal, is Cohen-Macaulay. Okay, so there we see a combinatorial property, right, corresponding to algebraic property. Okay, all right. So Knutson-Miller-Yong in 2009, in their study of Schubert determinantal ideals for 2, 1, 4, 3 avoiding permutations, introduced this notion of geometric vertex decomposition. So we talked about vertex decomposition of simplicial complexes. Geometric vertex decomposition is kind of an ideal theoretic analog of that. Okay, and so our setup, which is at the top of the slide, okay, is that we have an ideal which has a Grosvenor basis that looks like this, right? It looks like YQ1 plus R1, YQ2 plus R2, etc., and then H1 through HK, where Y doesn't divide any of the Q's, R's, or H's, okay? So we say this is square free in Y, okay? And in that setting, when we have this nice property of being square free in Y, or a Grosvenor basis of this form, okay, we can take the initial form with respect to Lex with respect to Y. Okay, so in my ideal at the top of the screen, right, if I Lex with respect to just the variable Y, I would get the form YQ1, and that might have lots of monomials in it, right? But I get the form YQ1, comma, YQ2, comma, YQL, comma, H1 through HK. Okay, and then you can decompose this ideal into, in Y is C intersect N plus Y, where C and N are as written on the slide. Okay, and this intersection is called a geometric vertex decomposition. And what's nice about geometric vertex decomposition, as Knutson-Miller-Yong showed, is that, well, Grosvenor bases sort of propagate. So if you have a Grosvenor basis for I, you get one for C and N. And in the homogeneous case, you can get the Hilbert series of I, S mod I, from the Hilbert series of S mod C and S mod N. And there are other nice properties as well, which I haven't written down. The idea is that they call it geometric vertex decomposition because it really does resemble a vertex decomposition of a simplicial complex. In particular, if I was a square-free monomial ideal, then this decomposition would be a decomposition into the deletion and the cone over the link. Okay. So here's an example of geometric vertex decomposition. Okay. So here's again that same simplicial complex that's showing up on the screen, and I'm seeing this as an initial ideal now, right? Because remember, geometric vertex decomposition is sort of about degeneration, Grosvenor degenerations, right? So I want to think of it as an initial ideal. The original ideal I that I'm starting with is at the top of the screen. It's this standard classical determinantal ideal of 2 by 2 minors of a 2 by 3 matrix. And I'm fixing a Lex order with X5 most expensive, not for any particular reason other than just to be consistent with what I had on the first slide. Okay. And if I look at the second bullet point after my simplicial complex, I can compute the X5 initial form. So I look at the first polynomial and I take the terms with the most X5s in it. So I get X1, X5 for the first polynomial, X2, X5 is the second polynomial. And then there are no X5s in the third polynomial of I, so I just keep that entire form, okay? And that's my initial ideal, okay? It's not a monomial ideal, right? I'm not degenerating all the way. I'm just lexing with respect to X5, okay? But then I can decompose this into two ideals, N plus X5 and C. And what you see is that if I were to degenerate all the way in this case, right, the N would become the deletion and the C would become the link. Okay, so really sort of this kind of motivates the terminology geometric vertex decomposition, because the algebra kind of really is kind of a sort of a shadow of a vertex decomposition. And in nice cases, not always, but in nice cases, the initial ideal really is the Stanley-Reisner ideal of a vertex decomposable complex. Okay, so that's geometric vertex decomposition. And so then again, sort of mirroring the situation for simplicial complexes, Patricia Klein and I sort of just extended in the natural way what Knutson-Miller-Yong did to define geometrically vertex decomposable ideal. And that just says I is geometrically vertex decomposable if it's unmixed. That's the analog of being a pure simplicial complex. Okay. And I is either the unit ideal or it's generated by indeterminates. So that's sort of the trivial case. Or we can find a geometric vertex decomposition where C and N are both geometrically vertex decomposable. Okay, so again, it's this recursive definition, totally kind of in analogy with the usual definition of vertex decomposition. And there are lots of things that are geometrically vertex decomposable. So in particular, Stanley-Reisner ideals of vertex decomposable complexes are, standard determinantal ideals are, ladder determinantal ideals are, Schubert determinantal ideals are, defining ideals of lower bound cluster algebras, certain toric ideals of graphs, which is the sort of the last third of the talk today. And one thing that is true, you can prove, is that if I is geometrically vertex decomposable, then I is radical. It's a radical ideal. And the polynomial ring mod, the ideal is Cohen-Macaulay, in analogy to vertex decomposability implying Cohen-Macaulay. Okay, so totally an analogy with vertex decomposability. But now this is sort of about degeneration. Okay. So sorry, I just see a question in the chat. Does something like this work on the Hilbert scheme of points in the plane by any chance? Yeah, so there, you mean like take an ideal of points and degenerate to like a monomial ideal? Is that
yeah, that's right. Like the whole thing gets, cut up into strata, and there's a monomial ideal in each stratum.
Yeah, right. So I think that's a little different here, because there you're going to have things that are very much non-reduced, right? You're going to get these like fat points.
Yeah.
And things are not going to be really square free in
no, nothing. Yeah, nothing square free.
Yeah. So
I want to stay in low, but drop square free.
Yeah. I'm not sure. Maybe I'll say a few words about, in the non-square free case at the end, but not that I know of. I don't know if anybody who's used sort of this idea there.
Okay, cool.
Yeah,
thanks.
Yeah, okay, so great. So we have this analog. All right. Oops. Okay. Oops, that's too far. Okay, there we go. All right. So no, it's not too far. Sorry. All right. So that was geometric vertex decomposition. And then the second sort of so that's the algebraic, that's supposed to be the algebraic combinatorics thing, because Knutson-Miller-Yong used it to study Schubert determinantal ideals, and it's been used sort of in the Schubert literature in other contexts since then. Okay. Gorenstein Liaison is supposed to be the commutative algebra side of the story. And I sort of adapted this slide from a really nice, a slide that Patricia Klein had in a talk where I learned for the very first time about Gorenstein Liaison. So I like how she introduces it. So this is due to her. Anyway, so or her slide. Anyway, so what is Gorenstein Liaison about? So let C1 and C2 be equidimensional subschemes of projective space. Liaison theory asks basically, if the union of these two subschemes is nice, can you transfer good properties from one to the other? Okay, so that's very vague. Just kind of like if you have a degeneration, you can transfer good properties of the initial scheme to the original scheme. Okay, so there's kind of a transfer, right, hiding I didn't talk about in the previous context as well. Okay, but liaison is sort of about transferring these good properties when the union is sufficiently nice. Okay, so in this example 2.4 here, we have, this is from Migliore and Nagel's Liaison and Related Topics, right? X is a complete intersection in projective 3 space of a surface of the union of two planes. X links the line C1 to a different line C2, okay? But for us today, sort of what does nice enough mean? It'll mean that C1 and C2, right, these two subschemes, share no common components and that their union is Gorenstein. Okay? And an example of a good property that you can transfer is the Cohen-Macaulay property. Okay, so just like, you say you have an ideal and it degenerates to a square-free monomial ideal, and you learn maybe because it's vertex decomposable that you're Cohen-Macaulay, you can say that the original ideal is Cohen-Macaulay. Here, if you can link C1 to C2 and C1 is Cohen-Macaulay, you can say C2 is Cohen-Macaulay. Okay, so again, you can transfer these properties. All right, so a little bit more on Gorenstein Liaison. What does it mean to be linked? Well, here's sort of just an algebraic version of what I just said. Let V1 and V2 and X be subschemes defined by homogeneous saturated ideals, okay, where X is Gorenstein, okay. If Ix is contained in the intersection of IV1 and V2, and if the colon ideals satisfy Ix colon IV1 equals IV2, and Ix colon IV2 is IV1, okay, then we say that V1 and V2 are directly algebraically G-linked, right? Colon ideals is about taking sort of the other components. So that's, again, an algebraic analog of what I just said about looking at unions of subschemes. Okay, so here in the context of the previous picture, V1 would be one of the subschemes C1, V2 would be the other subscheme C2, and X would be the union. Okay, so we say a subscheme V contained in Pn, or its ideal, is Gliecci if there's a sequence of G links from V to a complete intersection, and Gliecci implies Cohen-Macaulay. Okay, but there's an open question, which is sort of sort of an important open question in the theory, which is every arithmetically Cohen-Macaulay subscheme of projective space Gliecci. Okay, and sort of part of the aim of what I want to talk about, is to use geometric vertex decomposition to study this question in combinatorial settings. Okay. So we're going to get back to the combinatorics. So this is some commutative algebra. We're getting back to the combinatorics. But first, I need to tell you how are geometric vertex decomposition and liaison related. And well, Gorla, Migliore, and Nagel showed that some in subsets of these, that's why I didn't hyphenate them all, but they showed that many generalized determinantal ideals are Gliecci. And they use liaison to obtain Grosvenor bases. And before going any further, I just want to pause and say that in recent years, this Grosvenor basis via linkage technique, which is due to Gorla, Migliore, and Nagel, has been really successful in producing Grosvenor bases for ideals of interest to algebraic combinatorics. For example, Patricia Klein has done some work in this direction. On certain generalized determinantal ideals. My PhD student resolved a conjecture of Alex Young on Grosvenor bases for ideals defining open patches of Schubert varieties and the type A flag variety, all using this Grosvenor basis via linkage technique. So if you have combinatorial ideals and you think you know Grosvenor bases, but maybe you are trying to prove it, I suggest looking at, you might want to look at Gorla-Migliore and Nagel's work, because it's very nice. It's a very nice technique. Okay, but back to our comparison between liaison and geometric vertex decomposition. Nagel and Romer showed that Stanley-Reisner ideals of vertex decomposable simplicial complexes are Gliecci. So there's a connection in the simplicial complex setting. And Patricia and I showed that homogeneous, saturated, and unmixed geometrically vertex decomposable ideals are Gliecci. Okay. And in fact, there's sort of a correspondence between a vertex decomposition and what's called an elementary G by liaison, which gives these links. Okay, but I'm not going to go into that. Okay. But I've listed some examples of ideals that are both geometrically vertex decomposable and Gliecci, and it's the same list as before because geometrically vertex decomposables are Gliecci. Okay. So I want to shift gears then. That was sort of the first 2/3 of the talk. And again, the intention was just sort of to show you that this tool from commutative algebra, namely this Grosvenor basis via linkage technique, might perhaps be useful for you, because there's this nice connection, and it seems that many ideals in combinatorics that naturally show up. This is a very vague statement. Are maybe Gliecci because they're geometrically vertex decomposable, and so that's sort of where we're going in the context of toric ideals of graphs. All right, so this now is going to be work with my undergraduate student, Mike Cummings at McMaster, Sergio Da Silva, and Adam Vantal. Okay, so what is a toric ideal of a graph? Well, let G be a finite simple graph with vertex set V and edge set E. Oh, okay, sorry. There's some chat in the some comments in the chat. Okay, let G be a finite simple graph with a vertex set V of G and X in edge set E. Consider the homomorphism from the ring on the E's to the ring on the polynomial ring on the X's, where EI goes to xjxk, where EI is the edge xjxk. The toric ideal of a graph is the kernel of this map. So here's like a really baby example. Okay, it's just a 4 cycle. The vertices are labeled by the X's. The edges are labeled by the E's. Okay, and I've shown where each of the E's go. Phi1 of E1 is x1, x3, because E1 is the edge x1, x3, and phi of E2 is x1, x2, because E2 is the edge x1, x2. And certainly E1, E3 minus E2, E4 is in the kernel, and it turns out it is the kernel, or it's the kernel is generated by that element. Okay. So of course, more generally, you can get these quite complicated ideals generated by binomials, and these are called toric ideals of graphs. All right. So what can we say about toric ideals of graphs in Gorenstein Liaison? Well, sort of the starting point that we sort of took, and why partly I was interested in this question, comes from some results of Sturmfels and Hochster. And their results are more general, but it has these implications for toric ideals of graphs, which says let G be a finite simple graph and let IG be its toric ideal. If there's a monomial order such that the initial ideal is square free, then the polynomial ring mod the toric ideal is normal. And of course, that's very special, right? In general, it's not true that just because you have an arbitrary ideal and a square free initial ideal that you're going to be normal, right? Certainly not. But in the toric ideal setting, it's true. Okay. And then because following from a result of Hochster is if the polynomial ring mod the ideal is normal, then also it's Cohen-Macaulay. So implication of these two together is if there's a monomial order such that in IG is square free, then the quotient ring is Cohen-Macaulay. Okay, so it's totally reasonable then, right, in the context of taking that open question in liaison theory as motivation, right? Are all arithmetically Cohen-Macaulay subschemes of projective space Gleachy? It's totally reasonable then to say, okay, well, here's a really nice combinatorial class to study, toric ideals of graphs, which is with square-free initial ideals. Maybe we can use geometric vertex decomposition to show that they're Gleachy. Or maybe we're just interested in geometric vertex decomposition, period. Okay. And so sort of towards this Gleachy question, Constantinescu and Gorla in 2017 proved that toric ideals of bipartite graphs, which do fit into this class of having a square-free initial ideal, are Gleachy. Okay, so they don't make reference to geometric vertex decomposition there, but they give this very nice argument, a very combinatorial argument to show that these graphs are Gleachy. All right. So what can we say? Well, following Gorla and Constantinescu, we can use many of their techniques and results to show that in fact, their Gleachy result can also be obtained by first showing that IG is geometrically vertex decomposable and then using the fact that geometrically vertex decomposable ideals are Gleachy. But I mean, again, it's just sort of an adaptation of their argument. We can also show that if IG has a universal Grobner basis consisting of quadratic binomials, then IG is geometrically vertex decomposable and hence Gleachy. So that's a separate case. We can also obtain the Gleachy result and the geometric vertex decomposable result for large classes of graphs that are kind of built recursively by gluing cycles onto old graphs. Okay, so that's what the second theorem is about. So suppose H is obtained from G by attaching a cycle of even length to G along an edge. If the polynomial ring mod, the ideal is Cohen-Macaulay, then IH is Gleachy. Okay, and this follows from very quickly, actually, from a result of I think it's Migliore-Nagel, which is a very general result, a very nice result. But we also prove that if IG is geometrically vertex decomposable, then so is IH. Okay, so those are some results on geometric vertex decomposability of toric ideals of graphs. We can also get some further results just on liaison, which, I guess unfortunately, I guess, don't see the geometric vertex decomposition to the same degree. It's still involved in some of the proofs, but we don't get geometric vertex decomposability. And the results we get are, suppose G is a finite simple graph, IG its toric ideal. Okay. The first theorem says, suppose there's an edge containing a 4 cycle. Okay. And furthermore, we can take that edge sort of as most expensive in a monomial order and get a square-free monomial ideal. I don't care what the order is, as long as sort of Y is most expensive, then IG is Gleachy. And finally, as a consequence, we can use this result about the 4 cycle with square-free initial ideals to show that a class of graphs called gap-free graphs, which contain 4 cycles, are Gleachy. But I don't have a proof that they're geometrically vertex decomposable, though I suspect they probably are. So I think I'm out of time. So thank you.